Thanks everybody for tuning in today. We're continuing on with our Thrust B installment of the Urban Water Innovation Network Science Talk series. As a reminder, these presentations are really focused on the significant findings over the last 5 years of research projects with an emphasis on pragmatic recommendations for stakeholders and practitioners. So Thrust B really explores innovative technological solutions, and we're going to learn more from Dr. Smith today. So just as a reminder, we are recording these, and I have dropped the link to those recordings in the chat queue. That actually has access to every webinar that we've done over the lifespan of UN. So it's a good one to bookmark if you want it. At the end of the presentation, we hope to have a nice dialogue. So feel free to turn on your webcam and mic, or you can enter questions into the chat queue. And with that, I'm going to turn things over to Dr. James A. Smith, Professor of Civil and Environmental Engineering at Princeton University. Dr. Smith studies hydrology and hydrometeorology, the interplay of water and energy between the lower atmosphere and land in extreme floods. Jim's studies have centered on the development of technologies for measuring rainfall from weather radar, random modeling of the space-time structure of rainfall, and the microphysics of extreme rainfall. His research interests include flood hazards from landfalling tropical cyclones, thunderstorms in urban environments, and the transfer of heat in mountainous terrain. So with that, Jim, we can see your slides, and I know we can hear you, so take it away.
Okay, thanks, Sarah. Sorry for putting that up a little on the early side. So I'll be talking about the work we've been doing on flood hydrology and rainfall frequency and flood frequency. The image that I have here is from a storm in the Northern Virginia area, and it kind of highlights the type of events that I'll be looking at. It's a cloudburst in July of 2019. It produced rainfall accumulations at 1 hour time scale that were about 50% larger than the 1,000-year return interval values from the NOAA atlases. So I'll really be looking and focusing on the most extreme rainfall and going through kind of many of the technical issues that we've been developing, principally to improve tools for rainfall frequency characterization, but I'll show how that also translates into thinking about flood frequency as well. But I want to begin by instead of looking back, I want to point forward and highlight some of the key elements of flood hazard characterization that we will be wrestling with over the coming years. And let's begin. I'm going to begin with redfin. Some of you may not be familiar with redfin. It's a home buying tool, and it gives you information about homes that are for sale, and it'll give you information on every home in the United States. So it's an interesting tool for those of you that have looked into home buying. Now, one of the things, this is a screenshot from a house that just sold on October 29th in Alexandria. And it's a long page, but buried in it, beginning in 2020, is a flood and climate risk assessment. And for this particular property, it's severe, 8 out of 10. And this is new, and it in many ways it's groundbreaking. So you can go to any parcel in the United States and get your flood factor characterization of flood hazard. Now it's designed for home buyers, but more broadly, the group that is developing these tools, they're looking at changing the way we think about characterizing flood frequency. It's a nonprofit, the First Street Foundation, and they had worked closely with a group in the UK, Paul Bates Hydraulic Modeling Group, and his company Fathom. So there's a lot of hydrology and hydraulics. The real strength of this engine is the flood inundation modeling side. You see 8 out of 10. Now, on July 8th, 2019, this particular house had about 6 feet of water. And so it's the kind of property that's really subject to extreme flood hazards. And the first street or the flood factor characterization did a good job. But if you look around there, there are a lot of issues that come into play. And there are issues that pertain to the way you represent the hydrology of flood response. They are tied to the way you represent urban infrastructure. And then at the kind of the most basic, underlying all these are the NOAA Rainfall Frequency Atlas. So when they develop a 100-year floodplain, which goes into this characterization, it is really pinned off of the NOAA frequency analysis. Now they have tools, they'll tell you what your risk is over a 30-year mortgage. And so they have tools for projecting rainfall extremes into the future. And those tools in part draw on climate model simulations. So it's the package that we'll be looking at moving forward for both flood characterization and new rainfall frequency characterization. Now, New Jersey has a real problem with flooding, and it's one of the reasons that Senator Booker, along with Senator Wicker, Republican of Mississippi, introduced legislation last month, the Precip Act, which is specifically geared at revising the NOAA frequency atlases, revising the tools that are used for a high hazard rainfall characterization, probable maximum precipitation, and explicitly dealing with the impacts of climate change on rainfall frequency. So this reflects recognition that the frequency analysis tools that we are using are very much inadequate for the types of urban flood characterizations that we need. So this a paired piece of legislation was introduced in the House, also with bipartisan support. It's fairly likely that it will come into being, and it will, over the long haul, translate into a new set of tools and methods for rainfall frequency analysis. But very much at the forefront of this legislation is sorting out how we go about doing it. What's the correct path forward? So rainfall frequency analysis, from the municipal engineer to the U.S. Senate, it's recognized as one of the key elements of dealing with climate change, especially in the urban context. Now, climate change, sort of again going back to our Northeast setting, the remnants of Hurricane Ida brought home the potential consequences of climate change. Rainfall at 1 to 4 hour time period, again, that was much larger than 1,000-year return intervals. More than 50 flood fatalities, the bulk of them in New Jersey and New York. The first flood fatality of the day was in the early morning hours of September 1st, and it was in the Rock Creek Basin in near Rockville, Maryland, and it was in a basement apartment. Flooding in a basement apartment led to the first fatality, and the last was in a basement apartment in the Bronx in New York City on September 1st. And in fact, just an unacceptable number of the fatalities were in settings in which we should not be seeing flood fatalities of this type. So there's very much, in addition to the technical issues, there's very much an environmental justice component associated with the types of consequences we're seeing of the climate change and changing flood hazards. Now, to take it one step further, this is This is a map from the mayor's office in New York that shows the representation of the locations that were subject to extreme stormwater flooding. And most of the basement fatalities occurred in those settings. And so again, there's a technical piece, and I'm going to switch to talking about the technical piece. But in this case, it was known where the greatest hazards lay, and it was a matter of simply not doing anything about it. So those issues need to be pursued every bit as strongly as the revisions to the technical we use for flood hazards characterization. So stepping through the way we've looked at rainfall and flood frequency, one of the basic tools that we've been developing for rainfall frequency characterization departs from the standard NOAA tools, which are based on rain gauge observations and long rain gauge records. We've worked on tools that use high resolution rainfall fields derived from radar. Now, long records by radar standards, which in our case exceed 20 years. And the notion is that you trade space for time. And so we have resampling methods that take all of the big rain events within a region. And what's shown here is the Baltimore-Washington metropolitan region, where we would look at all of the events in this area and carry out a resampling method to develop frequency analysis results. Now, a key point is that this is not for points, but it's for drainage basins. And in the upper figure, you can barely see the outline of the Dead Run Basin. It's a 14.3 square kilometer watershed right along the Baltimore County, Baltimore City boundary. And so we're not looking at point rainfall frequency, but we're looking at rainfall frequency that explicitly includes the representation of the drainage basin. The bottom figure shows 1 hour, 3 hour, 6 hour precipitation frequency results for return intervals ranging from 5 to 100 years. So much of the work that we've done on rainfall frequency analysis has been looking at the sort of technical development of these tools. It's work mainly that's been done by Joyce Show and Mary Lynn Beck. It's one of the central contributions. Now, the technical elements deal with how you pick the regions. One I'll talk about a little bit more is it turns out rainfall varies. Rainfall extremes vary systematically over the region, and accounting for that spatial heterogeneity is really a key element of the work that we've carried out. So technical developments along these lines have been important contributions. Now, flood frequency analysis kind of comes for free in that you take the resampling of storms, you couple it with a hydrologic model, and you immediately have the capability of doing flood frequency analysis in addition to the rainfall frequency analysis that are carried out directly from the tools. Now, so flood frequency analysis, one piece of this is looking at what the elements of the urban environment are that really dictate flood response in a watershed. And so we've had a series of studies that address these questions. Brianne Smith, Joyce Show, again, Mary Lynn, again, carrying out studies in the Baltimore, Washington metropolitan area, Charlotte and Mecklenburg County, Phoenix being another important site where we've looked at these types of issues. The results here just show flood peak magnitude on the x-axis versus rainfall on the y-axis. And what we see is in watersheds in Baltimore, just a striking difference in peak flow for the same rainfall across different modes of development. And so taking these types of analyses and arriving at the key elements of representing the urban drainage system is an important part of the flood frequency. Now, going back to the Redfin-based analyses, they really don't account for much other than a bit of a look at impervious area. So that line of modeling is very much in need of tools that allow them to better accommodate the real stormwater system in urban areas. Now, one direction that we've looked at has been the sort of unique challenges of arid and semi-arid watersheds and their channel infiltration, and Tom pointed to this last week, is such an important element of the flow system. It couples with a theme in several of the studies looking at rainfall variability in time and space. In eastern humid watersheds, very different from arid western watersheds. In arid western watersheds, it really matters where the storm hits relative to the outlet of the drainage basin. Infiltration will kind of play a dominant role in dictating flood response. So this is a piece that looks at or has looked at the flood hydrology piece, translating into advances for flood modeling. Now, on the rainfall frequency side, and more broadly on the frequency side, we pursued a line that's along the NOAA precipitation frequency side, and that's basically you take annual maxima and you fit to a generalized extreme value distribution, and you use that to compute 5, 10, 100, 500-year return intervals. And this works for rainfall, it works for flood peaks, and then looking at the climate side, it also works for elements of the climate system, especially water balance components that are really critical for determining rainfall extremes. Yibing Su has carried out a series of studies looking at extremes of the atmospheric water balance using this path of frequency analysis based on the generalized extreme value distribution. Now, the atmospheric water balance, the storage term is precipitable water, units of depth. The transport term is the vertically integrated water vapor flux. The magnitude is of the vertically integrated water vapor flux is often denoted IVT, and it's a flux. It's a kilograms of water vapor per second per meter of cross-sectional area normal to the direction of flow. Now, precipitable water has really been kind of a dominant player in tools that look at design of high hazard structures, probable maximum precipitation. But it turns out that it's really much less important than vertically integrated water vapor flux and sort of dictating rainfall extremes. Now, Yibing's analyses here are based on 40 years of observations from the North American Regional Reanalysis. From those 40 years, for every grid in the domain, she computed precipitable water and vertically integrated water vapor flux, took the maximum value, and then carried out the extreme value analyses. Now, the thing that is distinctive about the generalized extreme value distribution, it has a location parameter, which is kind of a central tendency. It has a scale parameter, which is like a variability, and then it has a shape parameter, and that's what dictates upper tail thickness, how weird things can get. And the two extremes are when the shape is negative, you're bounded. There's an upper bound, and when it's positive, you have unbounded and thick-tailed distributions. Now, if you look at the analyses for precipitable water, much of the US is characterized by bounded distributions of precipitable water. It's kind of conceptually the way we think of things. This storage term, there's an upper bound that water vapor that you can put in a column based on temperature, and there are limits to how high temperature can get in the vertical. So it seems like precisely the kind of variable that should be bounded. Now, the right figure just shows what you get when you take the location, scale, and shape, and you estimate the 10-year precipitable water value. And we see this geographic variability with maxima between 50 and 60 millimeters along the Gulf Coast, and very striking spatial variability across the US. Now, in terms of kind of thinking about extremes, there are these little bullseyes of unbounded distributions. And it turns out that these locations are all associated with a particular hurricane. And so they're associated with a particular time in which the precipitable water was much larger than other values in the series. And that has a big impact on the way the extreme value distributions sort of look at the representation of frequency. So it's it's kind of an important way of thinking about climate. How do extremes drive our assessments of frequency? And so that shows up here. If you look at the vertically integrated water vapor flux, it's really more unbounded, especially looking along the Gulf Coast and into the eastern United States. And it reflects the fact that where you can come up with reasonable arguments for bounding the amount of water vapor in a column, when you put the wind into it, it becomes much, much more difficult to come up with reasonable bounds. And so that's one interesting element of the analyses, is that you're really looking at kind of a different world. From the hazards perspective, it is a setting in which if you've got large positive shape parameters, really weird things can happen. And I note this strange floods. There's a paper that we carried out that looks at all of the USGS stream gauging record. And there are settings in which you have record floods that are much larger than other floods, and they're very different from all the other floods. And this is a scenario that plays an important role in how we think about changing climate extremes. So in part, this is sort of methodology. The non-stationary GEV, you just allow 1, 2, or 3 of the parameters to vary with time, and the sort of common approach, and the one that Yi Bing looked at that worked quite well, is you just have the location parameter varying with time. Now, from the climate change perspective, and just looking at this 40-year record, there are significant increases in both precipitable water and vertically integrated water vapor flux over this 40-year period. Much of the area east of the Rockies is significant. The trends are significant at the 5% level, and the slopes, which are shown here, are sufficiently large to be of importance in thinking about the climate change impacts. And so this is the kind of setting in which a non-stationary analysis, in which you allow the location parameter to vary with time, gives better characterizations of the frequency quantity that you're looking at, whether it's rainfall, flood peaks, or elements of the atmospheric water balance. And so for rainfall analyses moving forward, this is what we plan to focus on, is analyses that work in this non-stationary GEV world. Okay, so that's a path of study that focuses on methodology, and it gets at some important issues to think about and how we deal with assessing changes in extremes. Now, another area that I'll just touch on briefly, but it was a big part of the work that we carried out, is how do we estimate rainfall accurately from radar? And so this, again, is work mainly that Mary Lynn and Molly Cheney carried out. So this is directed at these storm catalogs and then tools for assessing climate change directly from long radar records. And I'll just kind of highlight some important points. the radars in the US, they're polarimetric radars. There's this weird variable, specific differential phase shift. It's the best way of estimating rainfall. And so that's been an important part of what we've looked at, is demonstrating that for extreme rainfall. The figures that I show here, they are storm total from gauge and radar for the remnants of Tropical Storm Imelda in September of 2019. The top figure just takes the sort of standard parameterization of the algorithm, and there's just a systematic mean field bias. And from time immemorial and looking at radar, this systematic bias that varies from storm to storm has been one of the features that comes up repeatedly, and it's still an important part of the way that we deal with rainfall estimation when we're using polarimetric variables and when we're focusing on extremes. Conditional bias is an area that typically looks at what we see in the bottom figure, is that we just underestimate the largest rainfall accumulations, and why is that the case and how do we deal with that? And so that shows up systematically in analyses here, in analyses in Baltimore, and analyses in Phoenix and in St. Louis. It's an important part of the way that we characterize our ability to develop accurate storm catalogs for frequency analyses. And time varying bias just gets at, even over the course of the storm, things change, and things change in ways that systematically affect rainfall estimation accuracy. And so those are the topics that we focused on in looking at estimating extreme rainfall from radar. Very, very important part of the work that we've done, and one that sort of translates into many of the other analysis tools that we've carried out. Now, I want to segue a minute. So the analysis that I just showed, the great thing about Houston is the Harris County Flood Control District, almost 200 rain gauges, and that's why we were able to really develop good results there. Texas is the one place that NOAA has completed revisions to NOAA Atlas 14, so a version 2, which was completed in 2018, following so the series of catastrophic rain and flood events in 2015, 16, and 17. Now, the thing that that crops up here, this is the 24-hour, 100-year return interval. Rainfall varies from accumulates from 20 millimeters in Galveston Bay to less than 12 millimeters when you get close to College Station. And so you're looking at differences in rainfall that are on the order of, if you look at say a 6 to 7% difference in the rainfall extreme, you're talking about different distances that are tens of kilometers. And when we think about climate change, and we look at sort of Clausius-Clapeyron as sort of the foundation, and we think to 6 to 7% per degree, and we look at decades for a degree, one of the pieces that's missing from rainfall frequency analyses is this spatial dimension. In Texas, NOAA used the Harris County Flood Control District rain gauge observation, and then that's why they're able to kind of characterize this striking gradient. They don't have the same data for the Balcones Escarpment. You can see gradients there. They're probably much larger, but they don't have the rain gauge observations to resolve the differences in rainfall. So the big point here is that spatial gradients in rainfall, rainfall extremes, are likely as important as the climate change element of rainfall extremes, and thinking about how we go about dealing with our frequency characterizations. Now, it's a problem that occupied a lot of our time over the past 4 years. In the Baltimore metropolitan area, I'm just showing here a figure on the left. It's the mean annual extreme rainfall. So it's extreme, it's annual rainfall at rain rates larger than 50 millimeters per hour for an hour. And what we see through this analysis and a variety of other analyses is that there's a pronounced maximum in rainfall extremes that is northeast of Baltimore City and on the western boundary of Chesapeake Bay. Now, if you look at lightning observations, so for these extreme rainfall, it's almost exclusively convective rainfall and largely thunderstorms. And so we see the thunderstorm climatology sort of meshing with the analyses of rainfall extremes. So here too, spatial extremes or spatial gradients are large, but we don't have the rain gauge network, or NOAA doesn't have the rain gauge network to resolve these types of gradients. And so the NOAA precipitation frequency atlas for these regions, so very gradual changes in rainfall frequency. So this has been an element that we've looked at from an observational perspective. We've also looked at using numerical experiments. Yoonghee Ryu carried out some really interesting studies where she showed that the northeastern maximum in rainfall extremes, the area northeast of Baltimore, is tied to the interaction of the urban heat island circulation with the Bay Breeze circulation. So these features are important in characterizing rainfall extremes. If we're going to look at carrying out very detailed analyses of these types, we also need to understand mechanisms. And so in urban areas, it's understanding the effects of urban heat island, of urban roughness, and potentially urban aerosols. Long Yang carried out similar analyses for the Phoenix metropolitan area, mainly focusing on orographic mechanisms, also looking at irrigation and land surface processes and how that affected precipitation. So a big part of our activities looking at spatial heterogeneity of rainfall in and around urban areas. These are the areas that that we've worked on extensively, and although we continue to work on these problems, there's kind of a body of work there. What I want to talk about now are some analyses that that we've been doing and that we're continuing into this year. And one is work with Andy Miller, where we're looking at these long radar records, and we're trying to directly assess where and how short duration rainfall extremes are changing. So we have a 20-year record. The figure on the left, this is showing percent change in 10-year rainfall at 60-minute time interval. And just, reds are positive, blues are negatives. The evidence that we have at this point suggests that you really do overwhelmingly see increases in short duration rainfall extremes. Now, one of the things that comes up through these analyses, it's not as easy as you would think from the kind of coverage we see of all the big events. There's a lot going on that needs to be sorted out to be able to usefully characterize how rainfall extremes are changing. Now, in these analyses, we're looking at both the number of events exceeding thresholds and the amounts that thresholds are exceeded. And so we're trying to assess whether you're getting more events of a particular threshold or whether you're getting more extreme rainfall. And the bottom figure shows an analysis that Andy carried out where we couple the rainfall analyses with discharge observations. These are annual maxima of basin average rain rate and peak discharge from White Marsh Run. And Andy's conclusions are, again, the evidence is weighted toward increasing trends in both flood peaks and the rainfall that's associated with them. But it's kind of it's challenging to really pin that down in great detail. So ongoing work, and at our meeting over the summer, we'll have more definitive analyses there. We've been working on the real extremes and with the probable maximum precipitation as the target, and the sort of basic question, which has actually received surprisingly little attention over the last 5 or 6 decades, is what are bounds? How hard can it rain? And so that's been an area we've been looking at. And this sort of paired question is, how does it rain hard? The Baltimore, Washington metropolitan area is an interesting one. The world record rainfall at 1 minute is from Unionville, Maryland, which is very close to Ellicott City and the Tiber Run watershed that's shown here. 31.2 millimeters in 1 minute. That's a rain rate of 1870 millimeters per hour. The largest 15-minute rain rate, actually 515 an hourly, is from a tornadic storm in July of 1903. It was basically 50 millimeters in 15 minutes. The July 1903 was certainly a supercell, probably the case for the 1956 storm. And so one theme of this work is that supercell thunderstorms, the storms that produce tornadoes, are also the agents of most extreme rain rates. And supercell thunderstorms are thunderstorms that are rotating. And they're rotating at scales that are larger than the rotation of the tornadoes that they occasionally produce. And so this May 2018 storm in Ellicott City that devastated Ellicott City for the second time in 2 years was used as a model system. And I'll just quickly highlight the kinds of things that we're looking at with this storm. The analyses are based on polarimetric radar observations. So they're 3-dimensional slices through the cloud. There are 3 measurements. Reflectivity is the one you're probably familiar with. Differential reflectivity is just the difference in a horizontally polarized reflectivity and a vertically polarized reflectivity. It mainly is useful for getting at the types of hydrometeors you're looking at. And then KDP is this variable that's related to liquid water content. And so what we get out of ZDR, this differential reflectivity, is we get the updraft cores in the storm. And so on May 27th at 27 UTC, the storm is beginning to spin. And so from analyses of the velocity measurements made by the radar, we characterize how rapidly the storm is spinning. It begins spinning around 20 UTC and it spins up rapidly. That leads to this really striking updraft. Paired with the updraft is a downdraft that develops. And this melting hail with rain winds up being critical. Melting hail cools the atmosphere the same way in Arizona or the Front Range of the Rockies. Melting rain will cool the air. But you don't lose your water content, you just accelerate precipitation on the downside. So this tremendous downdraft is associated with melting hail. 2017, it's producing heavy rain. The updraft begins to shut off. The downdraft increases and to the point that you have extreme downdrafts preceding the cloudburst. So this cycle is the type of system that leads to the Unionville, Maryland type rain rates, or the rain rates that we experienced in Ellicott City in May of 2018. So pursuing those lines of analyses are ones that we're continuing to work on. And again, in the summer, we'll have more detailed results there. I wanted to end with Ida. So Ida produced record rainfall and flooding in a swath from Maryland up through Connecticut. Hurricane Ida is what we call it. So we had 1 to 4 hour rainfall accumulations, again exceeding 1,000-year return interval values based on the NOAA precipitation frequency. The figure here shows rainfall accumulations along the Pennsylvania-New Jersey border, the Neshannock watershed and Stony Brook, which drains Princeton, both experienced record flood peaks. The Neshannock was 50% larger than the second largest peak in a record of more than 90 years. Also a record flood peak in Stony Brook. Skillman here showing the polarimetric radar measurements at 15 minutes compared to the Skillman observations. The rainfall analyses are very good. The figure shows this almost 400 millimeter max of rainfall, principally over a 4-hour time period. So extremes are one element of it. And thinking about climate change, one piece that comes up with Ida is how are hurricanes changing? Hurricanes are the principal agents of floods along the Northeast corridor from Washington, D.C. Through New York City. The flood peak observations for the Neshannock show this series of hurricanes, Irene, Floyd, Agnes, Diane, and unnamed tropical cyclone. They're the ones at the top of the flood frequency world, and throughout the region, that's typically the case. They are all tropical cyclones undergoing extratropical transition. They're turning into extratropical cyclones. And so that's an important piece of the storms. There are a variety of ways we can think about Ida. It was a tropical cyclone. It was an extratropical cyclone. It had the vertically integrated water vapor flux that characterizes it as an atmospheric river episode. And it had multiple long track supercells, which produce most of the rainfall. Now, in trying to think about and wrap our head around the climate implications of Ida, we just haven't seen hurricanes producing tornadoes and supercells like Hurricane Ida. There's really no analog in the record, and so kind of a worst case climate scenario, especially looking at rainfall over time scales less than 6 hours, is this changing pattern of extratropical transition where we create a southern plains-like environment and induce clusters of these storms like the Ellicott City storms that produce rain rates on the very high end of what storms can do. So this is another line of research that we'll be working on over the course of this year, looking at how we frame this climate change problem that's going to be so important in developing tools for updating rainfall frequency results using climate model simulations. So with that, I would be happy to answer any questions that you have.
Great, thank you, Jim. Anybody have any questions?
I'm wondering, Jim, sort of how to selfishly thinking, like, so how do we rebuild the urban fabric to, particularly to deal with these Ida-like, these very extreme events, or Harvey in the case of Houston, where in Houston's case, they're seemingly a lot more frequent historically. That was quite a Texas graphic you showed.
Yeah.
But
yeah.
I'm just trying to think, like, we've sort of been in a process responding to the Flood Control Act where we've moved away from, newer development generally doesn't, we don't put streams subterranean anymore for the most part.
Right.
I'm just trying to think, like, what extreme events like this mean for the urban fabric of existing cities and future cities.
Yeah, and so I think for the way we focused is on existing cities, and right. And it's really putting cities between a rock and a hard place, because ultimately, if your stormwater system is not up to capacity to deal with these, then you've just got cascading problems to deal with. And so the and that's, that's the case in Alexandria, for example, a very wealthy community. Flooding is a big deal. The storm drains are undersized, but it's too expensive for a wealthy community to deal with.
Right.
So that's one piece of it. I think and so that one is going to require some really clever thinking, because the standard way of going at it is just too many dollars. I think the thing that we should be able to do is we should be able to better manage the hazards so that we don't see 50 fatality events the way we did.
Yeah, no, the both out of code basement apartments, as well as maybe more artfully written warnings. I mean, like people in New York were claiming they weren't warned, and I'm like, I'm pretty sure the Weather Service warned you. I guess it wasn't detailed and explicit enough. I'm not sure.
Yeah. Well, a lot of both in the ones I've looked at are Rockville, Maryland, and the Bronx, and I don't know if it is NOAA weather radio broadcast in Spanish, because these were immigrant communities.
Yeah,
and
I actually don't know the answer to that. That's a good point. Oh well, I know in New York too. It was a lot of Asian.
That's right.
Chinese immigrants was what I had heard.
Yep.
Yeah. Thanks, Jim. It was nice, as always. I always come away knowing a lot more about intensification processes and intense rain events. So,
Thanks.
Yeah.
Tom, that's quite the shirt you have on today.
Yes, this is normally my Friday shirt, but I've canceled class this Friday because I have to go to the field. So I wore it today for my class.
All right. I like it. That's some real university spirit there.
Well,
I have never seen a CSU shirt like that. So,
well, you guys don't have cactus, and you don't have the red, white, and blue color scheme of U of A. You have the green and white for CSU colors. So
that's true.
But you have the Ram, which Rams is a much better mascot than we're the Wildcats. It's just lame. I mean, even Jim's Princeton is Tigers. I mean, Wildcats is just like, well, which one?
Yeah, I was gonna say it's ambiguous.
Oh yeah, it's just horrible.
Claim them all.
Yeah.
All right. Well, thanks for your time, Jim, and thanks everyone for tuning in today. Obviously, we will take a break next week, and we will circle back on December 1st, I believe. Yes, December 1st. Okay. So take care, everybody. Stay safe and enjoy a nice holiday week next week.
Thanks.
Yeah, you too.
Thanks, guys. Bye-bye.
Bye.